Deep in the shipyards of Newport News, Virginia, the welding arcs never go dark. 100,000 tons of steel, $13 billion, 5,000 workers across 8 relentless years, all converging on a single machine of war, so massive it generates its own weather on the flight deck. But here's what no one tells you: even after all of that, the ship still can't touch the water. Not until it survives a final gauntlet of tests so brutal, so unforgiving, that they've broken multi-billion-dollar vessels before a single sailor ever stepped aboard. So what exactly does the U.S. Navy put a 100,000-ton aircraft carrier through before it's allowed to meet the sea? The USS Gerald R. Ford hull, classification CVN-78, is not just the largest warship ever built by the United States. It is, by almost every measurable standard, the most complex moving object ever assembled by human hands. At 1,106 feet long, with a flight deck spanning 4.5 acres, she displaces over 100,000 tons of seawater at full load. She carries up to 75 fixed-wing aircraft and helicopters, houses a crew of 4,500 sailors, and is powered by 2 A-1B nuclear reactors capable of generating 600 megawatts of electrical power. Before a single propeller turns, before a single F/A-18 screams off her bow, every inch of that steel must be proven worthy of the sea. Here's the number that stops engineers cold: 1/16 of an inch. That is the maximum allowable deviation in a structural weld on a nuclear-capable warship, roughly the thickness of a standard sheet of paper. Now hold that thought against 100,000 tons of steel, 2,600 compartments, and over 1 million individual welds across the entire hull. The Ford class was built using 500 prefabricated structural units called superlifts, each weighing up to 900 tons, assembled in sequence inside Dry Dock 12 at Newport News Shipbuilding. Every single joint where those units meet is a potential point of catastrophic failure. And the ocean has no sympathy for shortcuts. Inside the reactor compartment of CVN-78, there is almost no room to stand upright. The space is tight. The ambient temperature can exceed 100 degrees Fahrenheit during construction phases, and the psychological weight of working centimeters away from nuclear-grade steel is something no engineering manual prepares you for. This is where Huntington Ingalls Industries' non-destructive testing teams operate, running ultrasonic weld inspection across more than 2,000 internal bulkheads. High-frequency sound waves are fired through the metal, and technicians read the echo patterns on screen, hunting for voids, inclusions, or microfractures invisible to the naked eye. One missed defect in this compartment does not mean a warranty claim. It means a potential reactor containment failure at sea. Once the structural welds pass ultrasonic inspection, the Navy moves to hydrostatic testing, the most unforgiving integrity check in shipbuilding. High-pressure water is pumped into sealed compartments throughout the hull, held at pressures far exceeding anything the open ocean would generate. The logic is brutal in its simplicity. If a compartment leaks under controlled conditions on dry land, it will fail catastrophically under real-world stress. Technicians monitor pressure gauges for hours, scanning every seam for the faintest weeping of water. For a ship of CVN-78's complexity, this process involves hundreds of individual compartment tests run sequentially, documented obsessively, and signed off by Naval Sea Systems command inspectors who answer to no one but physics. The flight deck of an aircraft carrier is not designed to be comfortable. It is designed to survive violence repeated, scheduled, and deliberate. An F/A-18E/F Super Hornet lands at approximately 150 miles per hour, with a sink rate that slams roughly 30 tons of airframe and fuel into the flight deck surface in a fraction of a second. Before CVN-78 was ever cleared for flight operations, her deck underwent rigorous structural load testing, simulated impact loads applied mechanically to verify that the deck plating, deck edge supports, and underlying frame members could absorb thousands of these events across a 50-year service life. The deck coating itself, a non-skid surface applied in multiple layers, was tested for grip, thermal resistance, and chemical durability under jet exhaust that burns at over 1,000 degrees Fahrenheit. And yet, even after all of that, the USS Ford still wasn't ready. following what should have been final construction sign-off. Naval inspectors identified more than 20 significant technical deficiencies across the ship's systems. The most damaging was the Advanced Arresting Gear, the AAG system, designed to catch and decelerate landing aircraft. Repeated failures in the AAG's water twister energy absorbers triggered a 2-year program delay and cost an additional $780 million in redesign, testing, and recertification. The lesson was humiliating and expensive in a system this integrated. No single component exists in isolation. A flaw in one subsystem does not stay contained. It cascades. If this level of scrutiny applied to steel, welds, and deck plates already takes years and billions of dollars, stop and ask yourself, what does it take to bring the actual nuclear heart of this ship online for the very first time? The A-1B nuclear reactor, developed by Bechtel Marine Propulsion Corporation under the direction of naval reactors, is not an evolution of previous naval reactor technology. It is a generational leap. Where the Nimitz-class carriers ran on 2 A4W reactors, producing approximately 194 megawatts of thermal power each. The Ford-class A-1B reactors are designed to deliver roughly 3 times the electrical output of their predecessors and an estimated 600 megawatts of total ship service power. To put that in civilian terms, the 2 reactors aboard CVN-78 produce enough electricity to power approximately 100,000 American homes simultaneously. That power does not exist to run lights and air conditioning. It exists to electromagnetically launch 70,000-pound aircraft off a flight deck at 165 miles per hour using a system that did not exist on any previous carrier in history. The technicians who handle the A-1B reactor are not standard Navy engineers. They are graduates of the Naval Nuclear Propulsion Program, a pipeline so selective and demanding that it is widely considered the most rigorous technical training program in the United States military. Candidates spend 6 months in intensive classroom instruction at Naval Nuclear Power School in Goose Creek, South Carolina, followed by another 12 months of hands-on prototype training at an operational land-based reactor facility. By the time a nuclear-trained machinist's mate or electrician's mate is authorized to work on CVN-78's reactor plant, they have accumulated roughly 2 years of specialized education focused on a single piece of machinery. The program was built by Admiral Hyman Rickover, and it has not relaxed its standards since 1955. There is no shortcut, there is no waiver. Before the A-1B can ever be brought to life, it must first be fueled, and that process alone is a classified multi-week operation conducted under layers of physical security and federal oversight. The reactor core is loaded with highly enriched uranium fuel assemblies. The exact enrichment level is classified, but naval HEU is known to exceed 93% U-235, far beyond commercial reactor-grade fuel. The significance of the fuel load is staggering once sealed inside CVN-78's reactor compartment. That uranium core is designed to power the ship for its entire projected service life of 20 to 25 years without refueling. The Ford class eliminated the midlife refueling and complex overhaul, a process that cost approximately $2.5 billion and took 3 to 4 years for Nimitz-class carriers. That decision alone saves the Navy billions per hull over the ship's service life, but it also means the initial fuel load must be absolutely right. There is no second chance. Initial criticality is the most consequential single moment in the construction of any nuclear-powered warship. It is the instant when enough fissile material is assembled in the correct geometry, with control rods withdrawn to the precise calculated position, that a self-sustaining nuclear chain reaction begins. The temperature inside the reactor core begins to rise. Neutron flux detectors register the climb, and for the first time, the ship begins generating its own power from within. This event is not a switch being flipped. It is a precisely choreographed sequence executed by a crew following procedures that have been reviewed, validated, and signed off by Naval Reactors Headquarters in Washington, D.C. If any parameter deviates beyond its prescribed band during initial criticality, the sequence is immediately halted. Control rods are reinserted, and the entire evaluation process begins again from the start. After initial criticality is achieved, The reactor does not simply ramp up to full power. Low power testing holds the plant at just 1 to 5% of its rated thermal output for a period of several weeks. During this phase, every sensor, every valve, every coolant loop, and every instrumentation channel is verified against its design specification under actual nuclear operating conditions, conditions that cannot be fully replicated in a land-based prototype. The data gathered during low-power testing is not just a checklist exercise. It is the empirical baseline against which every future anomaly in the reactor's operational life will be compared. Naval reactors engineers analyze this data with a precision that borders on obsessive, because they understand a truth that cannot be overstated. A reactor problem on dry land is an engineering problem. A reactor problem in the middle of the Pacific Ocean is something else entirely. Here's the paradox that haunts every nuclear propulsion engineer who has ever worked on CVN-78. A single procedural error during the initial criticality sequence, a valve misaligned, a sensor misread. A control rod withdrawn beyond its calculated limit could trigger thermal events inside the reactor pressure vessel, severe enough to require complete removal and replacement of the reactor core. The cost of such a remediation on a Ford-class carrier has been estimated to potentially exceed $1 billion, not counting the scheduled delay. USS Ford itself suffered an 18-month delay, not from the reactor itself, but from the electrical power distribution system, the integrated network of switchboards, converters, and bus ties that connects the A-1B reactors to the ship's most critical new technology, the electromagnetic aircraft launch system, known as EMALS. The reactor could work perfectly, but until EMALS and the power grid could accept the load without destabilizing the entire ship's electrical plant, the Ford was going nowhere. If the reactor is the heart and the power grid is the circulatory system, then what exactly is the nervous system that decides when to fire, what to launch, and whether the ship lives or dies in combat? That answer is in the weapon systems, and what the Navy had to go through to get them online will genuinely surprise you. Everything about CVN-78's combat systems represents a deliberate break from 5 decades of carrier aviation tradition. The Nimitz-class carriers launched aircraft using the C-13 steam catapult, a system that worked reliably since the 1950s, driven by high-pressure steam bled directly from the ship's reactors. The Ford replaced all of that with the electromagnetic aircraft launch system, EMILES, a General Atomics design linear induction motor that accelerates a 70,000-pound aircraft from 0 to 165 miles per hour using a precisely controlled surge of electromagnetic energy. Simultaneously, the mechanical Mark 7 arresting gear that had caught landing aircraft since the Korean War era was replaced by the advanced arresting gear, the AAG, a water twister energy absorber, controlled entirely by software. And above the flight deck, the legacy AN/S, PS-48 and AN/S PS-49. Radar systems were replaced by the dual-band radar, the DBR, a fixed array system integrating an X-band AN/SPY, 3 multifunction radar with an S-band volume, search radar into a single integrated air picture. 3 revolutionary systems, all introduced simultaneously on the same ship. EMALS does not get certified by theory. It gets certified by repetition, brutal, documented, failure track repetition. Before any aircraft was ever placed on the launch shuttle, the system underwent 747 no-load and dead-load catapult shots at Naval Air Station Lakehurst in New Jersey, using weighted sleds designed to replicate the mass and aerodynamic drag of real aircraft across the full launch envelope. Engineers tracked energy delivery curves, end speed consistency, and peak load spikes with microsecond precision. The target was a system that could launch aircraft ranging from a 19,000-pound T-45 Goshawk trainer to a fully loaded 70,000-pound E-2D Advanced Hawkeye, with the same electromagnetic track, the same linear motor, adjusted only by software parameters. No steam valve, no mechanical setting, pure programmable physics. Here's the contradiction that defense contractors don't advertise. EMALS was specifically designed to be gentler on airframes than steam catapults. The old C-13 system delivered its energy in a violent Front-loaded spike engineers called it jolt that over decades accelerated structural fatigue in airframe components. E-mails was engineered to deliver a smoother, more linear acceleration profile, theoretically extending airframe service life by 30%. Yet in early operational testing, E-mails recorded a mission-capable failure rate approximately 4 times higher than the C-13 system it was designed to replace. The mean cycles between critical failures, a standard military reliability metric, fell far short of the Navy's required threshold. The system that was supposed to make carrier aviation more sustainable was in its early form, making it less reliable. The reliability problems were severe enough that in May 2017, President Donald Trump made a public statement suggesting the Navy should abandon E-mails entirely and revert to steam catapults on future Ford-class hulls. He cited the system's complexity and cost in a widely reported interview. The comment sent shockwaves through Naval Air Systems Command and the Huntington Ingalls Program Office. Engineers and program managers were subsequently called before congressional committees to defend not just the technology, but the entire acquisition strategy behind the Ford class. The counter-argument was technical and financial. Reverting to steam catapults would require a fundamental redesign of CVN-79, John F. Kennedy already under construction at an estimated additional cost exceeding $2 billion, while permanently capping the electrical launch capacity that the entire Ford-class power architecture was built to support. E-mails stayed. But the episode exposed how close the program came to an institutional collapse of confidence. Beyond the launch and recovery systems, CVN-78 required full integration of the Ship Self-Defense System, SSDS Mark II, with the Combat Direction System, the ship's central tactical brain. The CDS processes data from every sensor aboard and distributes a real-time tactical picture to every combat station on the ship. This system must simultaneously communicate via Link 16 data link with every escort destroyer, cruiser, submarine, and airborne asset operating within the carrier strike group, a network that in wartime could encompass 15 to 20 platforms spread across 500,000 square miles of ocean. The integration testing for this network alone consumed hundreds of man-hours of scenario simulation, with the Air Test and Evaluation Squadron 5X-23 from NAS Patuxent River providing the first actual aircraft F/A, 18 F Super Hornets, and E-2D Hawkeyes to validate launch, recovery, and sensor integration under real flight conditions during CVN-78's sea trials period. But even after E-mails fired clean, the AAAG caught reliably, and the combat systems talked to each other, the ship still had one final rite of passage to complete. One that is part engineering checkpoint, part national ceremony, and part irreversible commitment. The day the Ford met the water for the very first time. The christening and launching of a United States Navy warship is one of the oldest continuous military traditions in American history, a ceremony stretching back to the frigate USS Constitution in 1797. But do not mistake the pageantry for sentiment. On November 9th, 2013, as thousands gathered at Newport News Shipbuilding for the christening of CVN-78, the 72 hours preceding that ceremony had involved approximately 400 engineers running a continuous final inspection cycle across every critical system aboard the ship. Every watertight door, every bilge pump, every ballast tank valve, every hull penetration fitting. The champagne bottle was the public face of an event whose technical preparation was as exhaustive as anything that had come before it. Because unlike every test that preceded this moment, this one cannot be paused, reversed, or repeated. Mrs. and Susan Ford, Bale's daughter of the 38th President of the United States, Gerald R. Ford, served as CVN-78's ship's sponsor, a role in naval tradition that carries genuine ceremonial weight. It was her hand that swung the bottle of American sparkling wine against the bow of the ship, and her name that will be linked to CVN-78 for the entirety of the vessel's service life, potentially stretching to 2070 or beyond. The moment the bottle shattered, It marked the public completion of a construction phase that began with the keel laying in November 2009. But the engineers standing in the crowd behind the ceremony's formal platform knew that what happened in the next 6 hours would determine whether 8 years of work had been executed correctly or whether the world's most expensive warship would reveal a fatal miscalculation the instant she was asked to float. The flooding of Dry Dock 12 at Newport News is not a dramatic event to watch. It is slow, methodical, and nearly silent from a distance. Controlled inlet valves are open, and river water from the James River begins filling the dry dock at a carefully managed rate, approximately 15 million gallons over roughly 6 hours. The rate of flooding is not arbitrary. It is calculated to allow the ship's hull to accept buoyant force gradually, giving structural monitoring teams time to verify that the hull is responding to water pressure exactly as the finite element models predicted. As the waterline climbs the hull, observers track a single critical number, the ship's draft measurement against its design waterline, a tolerance of plus or minus 2 inches across the full 1,106-foot length of the hull. 2 inches on a structure the length of 4 city blocks. Simultaneously with the flooding sequence, a crew of electricians and pipe fitters is systematically severing more than 1,200 temporary connections power cables, compressed air lines, freshwater supply pipes, data conduits, and fuel lines that have connected CVN-78 to the shore infrastructure of the shipyard throughout her entire construction life. These connections are called umbilicals, and their disconnection is both a technical milestone and a symbolic one. From the moment the last umbilical is cut and the dry dock gates open to the James River, the USS Gerald R, Ford must sustain herself. Her own reactor plants provide power. Her own freshwater systems generate drinking water. Her own damage control systems respond to any flooding. She is, from that moment forward, a sovereign vessel incomplete, but alive and independent. This is a fact that the ceremony photographs never convey on the day CVN-78 was christened and floated out of Dry Dock 12. She was approximately 70% complete. The flight deck was installed, but not equipped. The island superstructure was in place, but not fully outfitted. Emails and AAG were present, but not operational. The A-1B reactors were installed, but not yet fueled. What floated out of that dry dock was an enormous functional hull, a proven structure, a proven buoyancy calculation, a proven weight distribution, but it was not yet a warship. CVN-78 would spend the next 4 years pierside at Newport News and at Norfolk Naval Station undergoing outfitting, system activation, and an exhaustive series of builders' sea trials and acceptance trials before the Navy formally commissioned her on July 22nd, 2017, nearly 8 years after her keel was laid. History does not allow the Navy the comfort of celebration without context. The USS Cole DDG-67, a guided missile destroyer, was attacked by a suicide bomb boat in the port of Aden, Yemen, less than 4 years after her own commissioning. 17 sailors were killed. The hull nearly sank. A warship is not proven by the elegance of its launch. It is proven by what it survives after. The USS Gerald R. Ford represents 45 years of evolution from the USS Nimitz, the culmination of a doctrine that says American power is projected not from fixed bases, but from 100,000 tons of sovereign territory that can position itself anywhere on Earth within days. That doctrine only holds as long as the ship and the people aboard her are ready for everything the sea and the adversary can produce. What you have seen across this entire process is not a ship being built. It is a nation's industrial capacity, engineering culture, and strategic doctrine made physical, forged in steel, tested in water, and proven under nuclear power. 8 years, $13 billion, 5,000 workers, and a tolerance of 1/16 of an inch. If that process, the sweat, the failures, the corrections, and the relentless standard of excellence that runs through every weld and every reactor procedure gave you a fundamentally different understanding of what American military power actually costs to produce, then leave a like as a recognition of the people whose names will never appear in any headline, but whose work holds the entire structure together. And if you want to keep going deeper into the truths behind the machines and the doctrines that shape the modern world, hit subscribe. The next time CVN-78's catapults fire and an F/A-18 clears the bow for the first time at sea, that story is worth telling in full.